Dear students, welcome back to my YouTube channel. And we were discussing about some topic from stereochemistry, and in this lecture I would like to discuss with you optical isomerism of lactic acid and tartaric acid, what is meant by enantiomer and diastereomer. So in last lecture we discussed in detail about the asymmetric molecule and disymmetric molecule or chiral molecule, and just recap that topic. And chiral molecule or asymmetric molecule is a molecule with no elements of symmetry of any kind is called asymmetric molecule. We have already discussed in previous lecture what are the types of elements of symmetry. And a molecule with non-superimposable on its mirror images are called disymmetric molecule or chiral molecule. A chiral object has mirror image, but at the same time which will be different from the original one. So it is like our hand, the mirror image of right hand is left hand, and we cannot superimpose the right hand with the left hand. And that is why it is called handedness. Chiral means the handedness. And optical isomerism means a chiral carbon atom bonded to 4 different atoms is a chiral center or chirality center. For example, 2-bromobutane and this carbon that is the red, it is attached to 4 different atoms, and this is chiral center. And here I have shown 2 isomers of 2-bromobutane, and all 4 atoms are arranged on this chiral carbon atom, and this is the one enantiomer of 2-bromobutane, and its mirror image is another enantiomer, and this one is the mirror image of the structure. So it has 2 enantiomers. At the same time, this another molecule I have shown, and you can see there is a plane of symmetry for this molecule, and this is not a chiral center. And how to draw the enantiomers? Enantiomers can draw either in perspective formula or in Fischer projection. What is mean by perspective formula? Perspective formula means it shows 2 off bond to asymmetric carbon in the plane of paper. For example, in previous example, 2-bromobutane, and you can see that 2 of the bond to asymmetric carbon, this asymmetric carbon is shown in the plane of paper. Suppose this is the plane of paper, and you have to show 2 bond in plane of the paper, and 1 bond as a solid wedge, that is this one, solid wedge, that will be out of the paper, and the 4th one, it is hatchet bridge, this is hatchet bridge, and this is behind the paper. So that is the one way of representing an enantiomer. And this is the mirror image of that enantiomer. Right, then another way, that is Fischer projection. Emil Fischer has proposed. In Fischer projection, it represents the asymmetric carbon, that is in this case 2-bromobutane, and the asymmetric carbon is the point of intersection of 2 perpendicular planes. So we have shown this one in 2-dimensional in Fischer projection, and there will be 2 lines, and this point of intersection will be the asymmetric carbon. So in this case this will be asymmetric carbon, and we have one horizontal line, and which represent the bond projected towards the viewer. And if you are viewing the molecule, and from here the bond projected towards the viewer will be the horizontal line, and vertical line usually represent the bond projected away from the viewer, and at the same time carbon chain drawn always vertically with C1, that is 1, 2, this is carbon 1 is this carbon is numbered as a 1, and this one is numbered as 2. Okay, so this is 2-bromobutane, and this should be vertically shown always vertically with the C1, that is this one, at the top. So this is the Fisher projection of enantiomer of 2-bromobutane, and in this case bromine is at the left, and here is mirror image, that is bromine at the right. So these are the two ways of representing an enantiomer. And what are the conditions of chirality? And there are some points which is to be remembered. What are the points? The presence of chiral center does not ensure chirality always. If there is only one chiral center in a molecule, it will definitely chiral. However, suppose a molecule contains more than one chiral center, many molecules, such molecules are chiral, but all of them are not chiral. For example, mesotartaric acid, we will be discussing in later part of the slide. And there are some chiral molecule that does not contain even a chiral carbon atom. For example, allenes. Such types of molecules does not have a chiral center, chiral carbon atom. Even though it does not contain chiral carbon atom, allenes are chiral molecule. So in general we can say the presence or absence of a chiral center is not a criterion for chirality, but the presence of chirality is a criterion for optical isomerism. And next we have to differentiate what is enantiomers and what is diastereomers. And enantiomerism or enantiomers are stereoisomers which are related to each other as object and its non-superimposable mirror images. So object with a non-superimposable mirror images. And at the same time, it rotates the plane polarized light to equal extent but in opposite directions are called enantiomers or enantiomorphs, and the phenomenon is known as enantiomerism. For example, this is tube-butanol. Tube-butanol has two enantiomers. It has one chiral center, that's chiral carbon. This is 1, 2, and third and fourth carbon will be shown here, and there is an hydrogen and OH. In one case OH is on right side and H is on left, and you can see that in other cases mirror images. And in this particular case, this is actually, it is called D2-butanol, that is, it is dextrorotatory. Dextrorotatory means it rotates the plane polarized light towards the right direction, and it is represented either by small d or the sign plus. And this structure is levorotatory, L2-butanol, and this is levo means it rotates the plane polarized towards the left, and it is represented by small l or minus. And enantiomers have almost identical physical and chemical properties. These are the same structure, only the difference is orientation. So it has identical physical and chemical properties, but they differ in the crystal shape and rate of reaction with other chemical compound and biological activities. And enantiomerism, we have to understand another term. It is called racemization or racemic mixture. What is meant by racemic mixture? In previous slide we have seen that there are two types of enantiomers, D and L. Suppose a compound contains equal amount of D and L, that is 50 D and 50 L, and in equal amount, it is called racemic mixture or racemic modification. It is represented by DL, it is small letter, or plus or minus, it is like this, which is actually optically inactive. Why it is optically inactive? Because the optical rotation due to one enantiomer is cancelled out by other enantiomer. D rotate to the left, L rotate to the left. So it cancel out in this particular case, racemic mixture. But at the same time, using suitable method, it is possible to separate this racemic mixture into D and L component. That is called resolution of racemic mixture. Next one, what is mean by diastereomerism? A chiral compound with more than one stereocenter. For example, 3-chloro-2-butanol. In this case, this is 3-chloro, that is starting numbering from here 1, 2, 3, 4. So 3-chloro-2-butanol. It contains two asymmetric centers, that is shown here, one this one and another this one. And how many stereoisomers are possible? Usually it is 2 raised to n. N means number of asymmetric center. So it contains two asymmetric centers, 2 raised to 2, that is 4. So 4 stereoisomers are possible in this case. That 4 stereoisomers, the Fischer projection of isomers are shown here. First case is called erythroenantiomer. Erythroenantiomers means the similar groups. It contain actually two asymmetric carbon. One is this one, and another one is this one. Okay, this one. Right, and there is a two hydrogen atom that is shown here on same side, and OH is shown right and Cl on right. And suppose similar groups are shown on same side, in side of vertical line, it is called erythro compound. And if this 1 and 2 are erythro, because the hydrogen atom, that is similar groups are shown on same side. But third and fourth, it is stereoenantiomers, because the same similar group, that is hydrogen, here you can see that, and they are on opposite side, so it is called stereoenantiomers. And you can see that there are 4 enantiomers for this compound, 2 erythroenantiomer and 3 and 4 2 stereoenantiomers. And in this erythroenantiomers, stereoisomer 1 and 2 are mirror images. You can see that these are mirror images, mirror plane. Suppose this is a mirror plane and these are mirror images. And these two isomers are non-superimposable. That means if you take this one and just drag it to this structure, this is structurally not same. So this is non-superimposable. That means therefore they are called erythroenantiomers. And stereoisomers 3 and 4, they are also non-superimposable. Therefore they are called stereoenantiomers. And at the same time, these are mirror images, right? These are mirror images 3 and 4, right? But at the same time, stereoisomers 1 and 3, that is this and this one. Similarly, 1 and 4, then 2 and 3 and 2 and 4, they are not mirror images of each other. And are not enantiomers. They are said to be diastereomers. So what is diastereomer? Stereoisomer which are not mirror images of each other are called diastereomer or diastereoisomer. So 1 and 3 and 1 and 4 and 2 and 3 and 2 and 4, they are not enantiomers, they are diastereomers. So what is the fundamental difference between enantiomers and diastereomers? Enantiomers means stereoisomers that are non-superimposable mirror images. Then diastereomer which are not mirror images of each other. And enantiomer will be optically active and diastereomers may be or may not be optically active. And enantiomers, it shows equal but opposite specific rotation. A diastereomer, it is optically active. Diastereomers show different specific rotation. And enantiomers will be having same physical property except the direction of optical rotation and crystal shape. But this diastereomers shows different physical properties. And enantiomers have same chemical properties and that react at the same rate with a given chiral compound. But diastereomers having different chemical properties and react at the same rate with a given achiral compound. And enantiomers, an equimolar mixture, that is purpose and D or L or plus or minus enantiomer, is optically inactive due to external compensation and is known as racemic mixture. But equimolar mixture of a pair of optically active diastereomers will not yield an inactive mixture. These are the fundamental difference between enantiomers and diastereomers. Next one, optical isomerism of lactic acid. This is the molecular structure of lactic acid. Lactic acid is having one chiral carbon, that is this carbon. So there will be two stereoisomers, or that is enantiomers, are possible with different optical properties. This is the structure of the enantiomers of D-lactic acid, and here COH and CH3 and for different atom hydrogen and hydroxyl group is attached to this carbon, and this is dextrorotatory, that is it rotates the plane polarized light to the right, and this is shown either by D or plus sign. And this one is a mirror image of this dextrorotatory lactic acid, that is levorotatory and L-lactic acid, and this is shown by small letter L or minus. And Fisher projection of lactic acid is like this, and here in first case OH is on the left and the carboxyl group is at the top, and this is first carbon, this is asymmetric carbon, and this is third carbon. So this is actually same as this one, and this is dextrorotatory lactic acid, and this is its mirror images, and it is levorotatory. And next one, this dextro and levo, both enantiomers have identical physical properties, that is both have same melting point 26 degrees Celsius. But at the same time, racemic mixture, that is the mixture of D and L form, has different melting point, that is 18 degrees Celsius. And both enantiomers show specific rotation of magnitude is same 3.8 degrees Celsius, and the direction will be different, that is D lactic acid will be plus 3.82 and L lactic acid is minus 3.82 degrees Celsius. And next one, optical isomerism of tartaric acid. This is tartaric acid, and this dicarboxylic acid with the two hydroxy group, and it has two asymmetric carbon atom, two asymmetric, and total stereoisomer will be 2 raised to 2, that is 4 isomers are possible. And these are the 4 possible isomers of tartaric acid, and usually vertical line we show the carbon, and H and OH you can show in first case a hydroxyl group at the right here in this carbon, and OH on the left in this carbon, and we can write another structure, second one OH on the left and this OH on the right, and these two isomers are the mirror images. Next one, we can show the similar groups on the same side of vertical line, that is hydrogen on same side and the hydroxyl group on the same side, and you can see that this is the fourth structure is just a mirror image of this structure, and there are 4 possible isomers, but we will study in detail. In structure 1 and 2 are mirror images, and 3 and 4 are mirror images, and you can see that 1 and 4 they are non-superimposable mirror images. If you take this to here or rotate 180 degree like this, and you can see that, and this has the different structure, non-superimposable, hence they are called enantiomers. And in this structure you can see that structure 1 and 2 diastereomeric with third and fourth, that is one is diastereomeric with the third and one is diastereomeric with the fourth, and 2 is diastereomeric with the third and 2 is diastereomeric with the fourth, and structure 3rd and 4th are superimposable mirror images. not non-superimposable, that is, it is superimposable. How? Because if you rotate this one in 180 degree, and you can see that if this is suppose I am putting this carbon as a star and this as a round, this carbon, and if you rotate through this plane of the paper, and you can see that this goes here and this star come here, and this circled carbon come here like this. But at the same time, and you can see that this hydroxyl group and the structure, the reverted structure will be same as third. So they are superimposable mirror images, you can say that. So hence they are, the third and fourth structures are same. And the same, one more thing, it has a plane of symmetry. That is, through middle, if you have this, through this plane, and you can see that these are same, and they have same structure. So this has a plane of symmetry, hence it is a chiral compound and also optically inactive. Such compounds are called mesocompound. The stereoisomers contain chiral carbon, but it is a chiral, and optically inactives are called mesocompound. So in total we can say there are only 3 optical isomers for tartaric acid, only 3 isomers, and this is shown here, these 3 isomers. One is, the first one is D lactic acid, that's small d, and the second in which OH is on the right, and here this carbon OH is on the left, and its mirror images, that is L lactic acid, and the equal mixture of this is called DL tartaric acid or equimolar mixture or racemic mixture. And the third isomer is mesotartaric acid, that is a hydroxyl group on the same side and having plane of symmetry. So dextrotartaric acid, D-tartaric acid, it rotate plane polarized light, this one to the right, and has no plane of symmetry. And levotartaric acid or L-tartaric acid, it rotate plane polarized light to the left and has no plane of symmetry. And at the same time, mesotartaric acid contains plane of symmetry and it's optically inactive due to internal compensation. That is the this one isomer, the optical rotation of this one will be compensated by other one. So it will be totally, it shows zero rotation. And these are the summary of the physical properties of the dextrorotatory and levo and meso compounds. And you can see that in the case of enantiomers, that is dextro and levo, the all properties are same, melting point is same, solubility is same, pK is same, density is same, and rotation magnitude is same, except that the direction is different. And in the case of meso, the rotation is zero. I already told you, and having melting point, different melting point from plus and minus form, and so solubility is also different, pK is also different. So dextro and levo forms are enantiomers. Both have identical physical properties but different optical properties. Only the difference is optical properties. Meso form is not a mirror image of D or L form, hence they are called diastereomers, and it has different physical properties. And in summary, we have learned the stereoisomers which are related to each other as an object to its non-superimposable mirror images, and the rotate to the plane polarized to equal extent but in opposite directions are called enantiomers. So enantiomers and the enantiomorphs, and the phenomenon is known as enantiomerism. And stereoisomers which are not mirror image of each other are called diastereoisomer or diastereomer. And optical isomers of lactic acid and tartaric acid are discussed in this module. Okay, thank you for watching.